Okay, it's time to start. So maybe first let me respond some queries about the coming midterms. I'll try to respond question in public. So even if you ask me in private, I will repeat it for the whole audience, right? Including those who are watching webcast. Okay, so first, just now somebody asked me whether this will be extremely difficult or no. I think each course have its syllabus, its content, right? So as long as you know, you have the knowledge, you pass the course, then why should I set it extremely difficult? But that said, it's obviously I cannot have everybody get A, right? So the university have this policy that there's a bell curve. So for those who are very good at math, and you take the course, how to say, by taking your own risk, right? So because the bell curve is there, then the cutoff had to be somewhere. So okay, so in other words, the probably is if you can do tutorials, you read lecture notes, and I'm sure you'll pass, right? So, but whether you can get A, it depends on how your friends perform. So this is a curve. Okay, I hope I answered the question. And also somebody asked me the help sheet or cheat sheet, whether it can be printed. Okay, so the short answer is yes, although I'm a little bit reluctant. But okay, so the reason for the cheat sheet is to help you summarize, right? So you have to summarize what you learned, and also we don't want to have a test on your memory, right? So you can write down something you want to memorize, or but anyway, so but if you think print it out is the best way you study, by all means do it. So as long as you know, you understand the material, I'm fine. I don't care how you do it. And what else? I'm thinking of the emails I receive. So lots of people are worried about ambiguity of language. So sometimes the question may have different readings, and so but for that I'll try my best to make it clear. Okay, and also I'll be around. So if you have concerns about the meaning, as long as you didn't ask me the answer, right? So as long as it's reasonable, I'll tell you, right? So it's not it's not a context of how to say. It's not a test of your language skills. It's general education on mathematics, right? So we care more about mathematics. Anything else you want to ask? Okay, so it seems everybody's happy. Okay, so then let's talk about mathematics. So we are this week we are talking about probability. So this is the second part of probability. So there are three topics. One is we are going to continue on some. I'll give you more examples. Concept related to like independence or conditional probability. So we'll see a little bit more examples. And then we are going to introduce a very important concept called expectation. And we'll have several examples on the expectations. And the last thing was very interesting. It's a kind of application or kind of fun things to know. So it's something called Benford law. I don't know how many of you know this. I don't know it. Only after I see the material, I know it. But it's fun. I search the internet. There's a very short clip of videos, and then we'll watch the 2 minutes or 3 minutes video and see what is going on. Okay, so so that's what I'm going to cover today. Okay, so let's go back, or let's try to remind ourselves something we learned on Tuesday. Okay, so we learned something called independent, right? So we are talking about events, we are talking about probability, and now we are trying to describe the independence of two events using probabilities, right? So the question, okay, so now here's an example. So the question for you is this. So there are 12 cars in a race, right? Okay, so let's call the Acura and Benz, just for A and B, right? So there are this car and that car. There are two of those cars. So each car has an equal chance of winning. Okay, so now let A and B be the events, that Acura and Benz win the race respectively. So in other words, let A denote the events that Acura wins, right? And B denote the events that Mercedes-Benz wins, right? So the question for you is, are the events independent? Okay. Okay, so we understand the question, right? So now the independence has an exact mathematical definition, right? So it has a meaning in mathematics. So let's follow that meaning, right? So observe that, so remember that when we define independence, we say if P intersect B is equal to the product of P and PB, and then we call them independent, right? So this is a mathematical definition. Okay, now apply to this course, this example. So P of A intersect B means both car A and car B win the race, but that's not possible, right? So there's no chance. So this is 0. Probability is 0. Okay. Now, how about the product of PA or PB? But by the condition, right? Each car has an equal chance of winning. So PA has 1 out of 12 chances of winning. Same for B. So the PA times PB is a product of these. In any case, it's not 0. So therefore, it fails the definition of being independent. So they are dependent, right? Is it clear? Well, our definition actually, obviously, comes from real life, right? So our independence should sort of related to the real life independence. So in real life, actually, so in this example, actually, it fits our common sense, right? Because surely there can only be one winner. So the two events are related, right? If A wins, then B cannot win. If B wins, A cannot win. So they are, in this sense, they are dependent. It's not totally, there's no connection at all, right? So common sense tells us is the case. They are dependent. But the mathematics also we have a solid mathematical argument saying that they are indeed independent. Okay? So that's a review of independence. Now, here I want to have two slightly more complicated examples. And okay, so I'll say, let's look at the statements and see why this is related to probability. Okay, so here. So there are something called false positives, and in the same way, there are something called false negatives. So the definition, the description is easy. So a false positive error, or in short, a false positive, commonly called a false alarm, right? So it is a result indicate a given condition exists. Actually, it is not, right? So suppose you test whether you have some disease. Although you don't have the disease, they give you a false alarm. They say you have the disease, right? Something like this. So that's false positive. Okay, so for example, I don't know. I took it from Wikipedia. So it says in the legend or the fairy tale, a boy who cries wolf, right? So the condition. Okay, so there is no wolf, but this kid somehow he cheats, right? He say there's a wolf and he cry wolf wolf. So this is an example of false positive, right? There's no such situation, but somehow the test or the person announced there is such a situation. So it's false positive, okay? Now symmetrically you could have false negative, right? So in real life, so it's you do have the situation, but somehow the test or the person failed to observe this. So it's a false negative, right? So again, Wikipedia gives something like this. So maybe somebody was truly guilty, but somehow he escaped. So I mean, he is acquitted, right, of a crime. So this is he does he did something terrible, but somehow the law didn't catch him, right? So this is a false negative. But in today's example, let's just talk about false positives. Okay. All right. So this is probably artificial example. So we have some person, let's say Miss Wong, says she is itchy. There's a test for allergy to cats. Right. Somebody, I mean, if they are close to a cat, they feel itchy. Right. Okay. So, but the test somehow is not always right. Okay, so here's a condition. So for people who really do have the allergy, the test says yes 80% of the time. So the test is accurate up to 80% for this group of people. Okay? Now for people who do not have the allergy, the test say yes 10% of the time. So these are the false positives, right? So they do not have this symptom, but the test says yes, you have. Is this okay? So now what is our question? So now suppose in the population, only 1% people has the allergy. And somehow for Ms. Wong, the test says yes. Okay? So what is the chance that she really has the allergy? This is complicated, right? So how do we know that? Is the question clear? Okay, you may not know how to solve it yet, but the question is like this. Okay. Okay. So now, why? so the solution is actually this is an exercise on conditional probability. Right, so we have to read, we have to get the information from what is stated in the previous slides and write them in terms of probability. And this probability somehow involves something called conditional probability. Okay, so let's read it. So let's first name the events. So let A be the event of someone having allergy, and B be the test saying yes, right? B will be the event that the test says you have the allergy. Now we want to find this is a conditional probability. So under this condition B, right? So suppose the test says yes. What is the chance you actually have allergy, right? So is this okay? So the conditional probability says we shrink our sample space, right? We only look at the events where B happens. Then inside this event B, what is the portion of A? So this is the conditional probability. Is this all right? So we want to find this. Okay. Now we have to read the data. So what data do we have? Okay. So here, so first, the probability of event A happen is 1%. Right? Event A says someone has this allergy, but we know. Sorry, I cannot fit everything in one slide. So, so we know that 1% of population have the allergy. So the probability for A happens is 1%. Okay. So here we have PA is 1%. Okay. Now, now how about this A and intersect B? You see, we are going to compute this conditional probability, and then we need to find those intersections, right? The probability of the intersection. So now what is the P of A intersect B? So it says that, so sorry, I have to go back here. So for the people who really do have allergy, this is the people having A. Event A happens. The test says yes 80% of the time, right? So you have 80% for the 1%. A is the 1%, and among the 1% you have 80%, 8%, 80%. Yeah, sorry, you have 0.8 times this, so it's this. Okay, right? So let's move on to the next line. So maybe jump. Let's skip this line for 30 seconds. So we want to calculate the conditional probability of this. Under the condition B, what is the probability of A? Right? This is PA stroke B. Now, by definition, it is we shrink our sample space to B, so it is out of P of B, what is P of A intersect B? Right? So we want to find this. Now, the first line here, we find out the denominator. We know the A intersect B already, right? Now the question is, what is P of B? We don't know yet, right? So let's find it out. So here in the tutorial problem, you'll see that P of B actually is P of A intersect B plus P of A complement intersect B. The reason is event A happen and not happen is 100%, right? So therefore, you have this equality. Okay, so P of B will be P of A intersect B plus P of A complement intersect B. Okay, now if you know how to calculate P of A intersect B, which is this, you know how to calculate P of A complement intersect B, right? So that is among the people who do not have the allergy, which is the A complement, right? How many of them tests will say yes, right? So we are here. So it's 10% for the group of not having allergy, 0.99. Okay. So if you add these, you get the probability of B, which is this, 0.107. Is this okay, right? So we are okay, right? Okay, so then you plug in the number here. So P of A intersect B is this number. So you copy it down there, and then you copy it down there. So it's roughly 7%. So that's the answer. Okay, so these things are not so direct, right? So you have to look at the data and figure out what it says. Okay, okay, if you are from statistics department or you are good at statistics, so you probably know some more advanced ways, but that's not my job, right? So if you know more, okay, by all means use your theorem Bayes or whatever. You can use something else to solve. But I hope this is reasonable enough. Okay. So now let's look at one more example. Then we move on to the other topics. So this is again sort of related to false positive and so on and so forth. Okay, so let's look at an example. So this example says a taxi, was involved in a hit and run accident at night. So something terrible happened, a taxi hit a person. Okay, so there are only 2 cab companies in the city. Okay, so the green and the blue, let's say, right? So there are two companies, and each cab is equally like, so the taxi driver, they can have accident equally likely, right? So there's not like this company will have lots of hitters and these companies. So let's assume that they have equal chance, right? The accident happens, I mean, it's possibly happen to everyone in the equal chance. Okay, so the following facts are known. Okay, so we set the scenario in this way. Okay, so we know the data. We know that 85% of the cabs are green. So green company is larger. It has 85% of the taxi. And the remaining 15 belong to the blue company. Okay, so this is one data. Now the witness identified the cab as blue. So you question some witness. So who did this hit and run? So the witness says blue. Okay. And then, so here is the other piece of information. So the court tested the reliability of witness and so on and so forth. So the data goes like this. So the witness correctly identified each of the 2 colors 80% of the time, and failed 20% of the time, right? Because it's dark in the night, and so sometimes you cannot really see blue and green, and so 80% it correctly identified, and the other 20% somehow is wrong. Okay, so these are the data. Now, based on these data, the question for you is, what is the chance that the cab in the accident is blue? Right? So the witness says he's blue, but the guy could be wrong. Right? 80% is right, 20% is wrong. So this is again a question about false positive word. Okay, so now we have to, since we have done the first example, so we do the same thing, right? So we have to formulate this question in terms of conditional probability, right? So then we look at what do we know, right? How to read, how to interpret these data, and then do some calculation to find the answer. Okay? Okay, so let's try. Again, let's name the events. So let A be the event that the blue cab was involved in the accident. So it's the blue guy who hit. Okay. Let B be the event that witness identified the cab as blue. Okay. So what do we want to find? So we want to find the probability of this under the condition B, A happens. Let's see whether this is correct, right? So we want to know. So now the previous slide says a witness says it's blue. So the witness identified the cab as blue. Now we want to find under this situation, under this condition, someone identified the taxi as blue. What is the probability that really it is a blue cab involved in the accident? So it's the conditional probability of under the condition B. What's the probability of A? Do you agree? Right, this is reasonable, right? So, okay, so then we have to read the data, see what the data say, right? So the data says we know that the probability of a blue cab involved in the accident is 15%, because we say it's equally for car hit the passenger or whatever. So now they are 85% is green. So the 15% for the accident was caused by the blue one, right? And by the same reason, the A complement is the green taxi. So they are they dominate the market by 85%. So the probability of the green did the accident is 85%. Okay, so we have the probability of A is this, probability of A complement is that. Okay. Now we also know the so look at this information. So you also know that the probability of the witness correctly identify the accident. So the reading is this. So remember the A says it is the blue cab commits the crime. Now under this situation, there's 80% of chance the witness correctly identify, right? Meaning the witness says it's blue. Okay, let's look at this data again. So A says it is the blue who commit the hit and run, and B says the witness identify it is blue. Now from the part I just showed you, it says witness correctly identify each of the two colors 80% of the time. The word correctly identify means if it's blue commit the hit and run, the witness correctly, right, also say it's blue, right? So the conditional probability is 80%. Okay, so we are here, and there are 20% of chance it got it wrong, right? So in other words, it's the green guy who made the hit and run, but the witness says blue. So under the other condition is 0.2. Okay, so this is the analysis of the data, how to read the data. Okay, now based on these data, can we get this conditional probability? Well, you have now, it is one step more complicated, right? Because we need to know what is P of A intersect B, right? So therefore, you have to solve some equations, and but that's not too bad. Okay, so let's try this. So we know that P of B stroke A, this is the conditional probability, is 0.8. So by definition, this is the conditional probability is P of A intersect B divided by P of A. Right? This formula we use several times. Okay, so this is 0.8. We also know the denominator, right? P of A somewhere here is 15%. Okay, so from these two, you can solve the numerator. P of A intersect B actually is the product of these two, right? So hopefully this is correct. This 0.12, 12%. Okay. Okay, so similarly, from the other piece of information, so P of the conditional probability of B stroke under the condition A complement is 0.2, right? So in other words, we have this one. So it's the probability of the intersection divided by the probability of this, what you restrict to, right? A complement. So this is 0.2. And we also know the probability of A complement is 0.85, right? So we know this. So we can figure out these, the probability of A complement intersect B is 17%. Okay? Okay, finally, we want to have the conditional probability of P of A under the condition B, right? So this is what we want to find. You all agreed, right? So by definition, this is A of P, is P of A intersect B divided by P of B, right? So now we use the same trick. Once we have P of A intersect B and P of A complement intersect B, we can figure out POB, which is the sum of the two. Okay? So this part actually is POB, which is what we want, right? Now we know this is, where is it? One is 12%, the other one is 17%. You add them up, you get 29%, right? This is, so if you calculate the ratio, you get 41%. So the answer is 41% to get it right. Okay, so it's interesting, but somehow it's complicated. Okay. All right. So now, questions or? Okay. So now let's move on to the main topic of this lecture. So we want to talk about expectations. So this is a very important concept in probability. So this is much more important than the false positives. Okay, so this is really important. Okay, so now to motivate you, so let's look at the example and see. Then later, after we learn expectation, we'll solve this question. Okay, the question like this, right? So you are given the following two options. So don't ask me why you are given this. Right? Somehow somebody like to do this. Okay, so either you accept $1,000 now. Well, of course we are happy, right? So we want to. And the other option involves probability. So you flip a coin, but this coin is biased, is loaded, or so the biased coin does this. So there are 90% of chance to get head, and 10% of chance to get tail. Okay. Now, if you get the lucky 90%, you get 1,200. You get more money. Now, suppose you are unlucky, you get the tail in the 10%. Not only you don't get any money, you get minus. I mean, you have to pay the guy $100. Okay. So now, this is an artificial scenario, right? But suppose you are offered like this. Now the first question is, right, which option should you take? Suppose you have one chance, right? Which option you should take? But now more related to the expectation. So here is a more related question, question 2. So if you know you will be made this offer every day for the for the whole year, so the offer was repeatedly in front of you, right? So which option would you pick? This artificial, but let's imagine that, right? Suppose you can do this thing over and over again. You can repeat. Now, what should you take? Okay, we will come back to this. This is an easy example. I'm sure lots of you already know, but we will come back to this. So this has something to do with the expectation. Okay. Okay. So now to say the expectation, I have to introduce some big words called random variable. Last time we already see it. Okay. Of course, one can say things without using the big word, but this word random variable expectation is so common in probability. So let's just introduce it. It's okay. So we have seen it once actually, but let me just introduce the same thing again. If you feel the description is hard to digest, look at the examples. The example is simple. Okay, so let's try. So sometimes we are interested in functions from sample space S to real numbers. This is hard to digest. Right? We refer to those functions as random variables. It's weird. So on the face of it, you would think random variable is a variable, but no, it's not variable. It's a function, right? And the function from some space to somewhere, which is strange, right? But never mind. Okay, so let's look at some examples, right? So for example, suppose we toss a coin n times. Okay, so the sample space has 2 to the n many elements, right? Each element is a string of length n, consists of head and h and t's, right? For example, you have HT, 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 right? So you could have this for a while, or you can have purely all head, or so it's just each point in the sample, each outcome, just record the result of the coin tossing. Okay. Okay. So now, what is let's consider a function, right? So let's consider this function. So this function will define on the sample space, and then return us a real number. Okay, so in this case, okay, in most of the cases, it will return us a natural number, but natural number is also a real number, right? So this is let's consider this function. So this function called x. So this function, the domain is a sample space, and it will return us some value, some number. So the number is defined by counting the number of heads appear in the result. Right? So for example, suppose suppose is HT, 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 right? So the result most likely is just half n, right? Let's say n is even, right? So you just count how many heads appear. Suppose everything is n, everything is head, then the value is n, right? So this so-called random variable will look at each event and return you a number. So this number in this case, in this example, is the number of heads in this event. Okay, so example is easy, right? So okay, so well, I have to say the random variable, if you look at the exact definition, is more complicated. But this is GE, right? General education. So we'll consider very easy case. So all the sample space are finite, right? In like toss a coin for 3 times, or so in probability you'll see that this is some kind of measurable function or some measurable space, or those horrible things. But we will look at things just like this. Okay. Okay. So we can see a little bit more examples so that let's feel more comfortable about random variables. Okay. So here's another example. So suppose we toss 2 dice. I don't know. Maybe I should delete this S. Okay, 2 dice are tossed. So the sample space has 36 elements, right? Because it's a combination. For the first toss, you have 6 possibilities. Second toss, you also have 6 possibilities. So altogether, you have 36, right? So the result could be 4, 5, 6, 6, or 3, 1, 1, 2, or so these things. Okay. So now I want to define a random variable. So I want to define a function. The function on each point, each result, each point, each element in the sample space will return me a number, right? So this time I ask him to give me this number. Give me the sum of the 2 numbers obtained, right? Suppose you toss the dice twice. Suppose you get 1, 2. The random variable will give you the sum, so it's 3. Right? Suppose you toss 2, 6. I mean 6, 6, and then the random variable will give you 12. Okay, so this is a now what is the range of this random variable? You cannot get 1 because you toss the dice twice. So the smallest thing you can get is 1 and 1, right? So the smallest thing is 2. The biggest is 12 because you can 6, 6, you get 12. In between, all combinations are possible. So therefore, the range of this random variable is this. Okay. Now this is a slightly more mathematical example. So a number is picked from this set. So the integers from 1 to 100. So I have 100 integers to choose from. Now let's define a random variable so that the random variable will give the number of factors of the number you choose. Sorry, we pick a number, right? So the sample space is a number, 1 out of this 100, right? So the random variable will send the number we pick to another number, right? So for example, so let me repeat the definition. So x will return the number of factors of the number you choose. For example, if we draw 14 here, so we'll get 4. Why? Because how many factors of 14? So 14 is 2 times 7, right? But if you count factors, 1 also divide 14. So the number of so the factors of 14 are 1, 2, 7, and 14. Right? So there are 4 factors. So this random variable, again, don't ask me why, right? It just does this. Okay. You give me a number, I'll return you the number of factors. Okay. For example, you choose 7. So what is the random variable returned to you? For 7, 7 is a prime number. It can only be divided by, it only has 2 vectors, 2 factors, 1 and 7, right? So the x of 7 is 2. Okay? Is this? And in the homework, I will ask you what is the range of x. This is slightly more challenging than the earlier one. Okay? So how many factors? Okay. All right. So this is a random variable. Now, random variable is related to probability also because we are talking about okay. Since the value of random variable is determined by the outcome of the experiment, we may look at the probability to the possible values of random. Okay, so don't worry about what I said there. So this is the example. Okay, so I want to measure how likely certain event happen. The event will relate it to the random variable, right? So for any a in R, we define the probability that the random variable give me value a to be this. So the notation is the probability of x equal a. Because, x always return a number. So I choose my favorite number. So I want to know what is the chance of this random variable give me that number, right? So P bracket x equal a denote the probability of this set. So the outcome in the sample space such that the random variable give me the a here. Okay? So notice the right-hand side here, it makes sense. Right? I'm defining the left-hand side using right-hand side. So the right-hand side actually makes sense. Why? Because you see call this set in the bracket S sub a because it depends on the number a. You give me an a, I give you a probability. You give me a prime, I give you probability prime. I'll give you another probability, right? So you give me a1, I give you probability 1. You give me a2, I'll give you another probability a2, p2, right? So let S sub a denote the set here. In other words, S sub a is all the point in the sample space so that the random variable will send it to a. We'll see examples in the next slide. Okay. Okay, so this is a subset of S, right? Because, well, you collect points in S. So this is a subset of S. So therefore, it is an event, right? Event is a subset of the sample space. Now, for any event, the probability makes sense, right? We know we take probability of the events. So when I say I take probability, so the event x equal a actually is this set, is this event. Okay? Look at the examples. Example makes things easier. Okay, for example, let's toss a coin 3 times. Okay, so let x denote the random variable which counts the head. Okay, so the range will be either 1 or 2 or 3. There's 0, possibly 0, right? So let's look at the probability of the event x equals 0. Now, in this example, x is the number of heads. So x equals 0 means there's no head, all tail, right? So this is the event. Okay, I dropped the set. Okay, but you understand what I'm calculating. So you're calculating the event where the 3 toss all give you tail, right? So this is 1 out of 8, right? The size of sample space is 8. And in this case, there's only one chance that you don't have any head. The counting of the head is 0, so you have 1 out of 8. Okay. Similarly, how about the probability of this random variable equal 1, x equal 1? Well, there's only one head, so there are 3 possibilities, right? The head is appear at last toss, second toss, first toss. So 3 out of 8. Okay, and then similarly you have. But remember the probability, all possibilities add up 1, right? The total probability must be 1. So if you add, indeed, it's 1. Okay. This is okay. So, okay. Now, once you are familiar with the big word random variable, we can talk about the expectation of this random variable. Okay. So definition: if x is a random variable, okay, the expected value or expectation of x denoted by capital E, right, for expectation. E of people always use a square bracket for some reason. Okay, E of x is defined in this way. So E of x is the sum of the value small x times the probability that x hits this small x. We'll see examples. Okay, so because we always consider finite sample spaces, so actually you can do this. So suppose you only have finite possibilities, so you look at each possibility and just add them up, right? So you do this. Suppose x can take some value, a1 up to a5, for example. And then you say you use a1 times the probability x equal a1 plus a2 times the probability x equal a2 and all the way to a5 times the probability x equal a5. That is your expected value. Okay, we'll see examples. So the explanation for this EX is the expected value of x is a weighted average. Weighted average means you multiply some number and take average, right? So weighted average of the possible values that x can take on, right? For example, here the small x are the possible values x can take on. And each value being weighted by the probability. So the weight you put on the small x is probability. Well, if this paragraph doesn't help, look at the examples. Okay, so here's an example. So we have several examples. So this is our main topic. So, okay, so a vendor sells 50 bottles of drink on a hot day, like today. Today is a hot day. 30 bottles on a normal day. I don't know, maybe. And 15 bottles on a cold day. So it never happened in Singapore. No cold day, but okay. So now the profit he make from his business is 60 cents, right? So he somehow buys each bottle for 20 cents and then he sells for 80 cents, right? Okay, so And the random part comes here. So the probability of the day is hot, normal, and cold like this. So there are 30% being hot, 50% being normal, 20% being cold. Okay. So now we want to find the expected daily profit from the guy who sells the drink. Okay? Okay, so now what is the random variable? The random variable is the profit, right? So let X be the daily profit. So we know that on a hot day, the X is, he sells 50 bottles, right? So for each bottle, he has 60 cents. So he has, I don't know, $30, okay? And on a normal day, he can sell 30 bottles. And again, you have certain profit margin, so you get this $18. And a cold day, he only sells 15, so he get this amount of profit. Okay. We also know the probability of the hot day, normal day, and cold days like this, right? 30% hot day, 50% normal day, 20% cold day. So what is the expected value? So we have to use the amount, the value of X take. For example, here X equal 30. X equals $30. X equals 30. Now the chance of that happening is during hot day, right? So is 30%, right? So this is the P equal $30, and the 0.3 is the probability of that happening. Okay, so this is one component of the weighted sum plus the other one, right? So the profit margin is 18 plus the probability you get X equal 18. So that is the probability of a normal day. So this is the 0.5 multiplied this. And then the same for the cold day. Okay? So this will be the expected value. So this is a weighted average of the three things. So you get this amount. Okay? Let's see one more, then we take a break. Okay? So after break, we continue to see a little bit more. Okay? So the next example of expectation is we toss two dice, right? And we want to find the expected value of the total score. We want to find the sum of the dice, the number you get. Okay, so let X denote the random variable that return us the score obtained by two dice, the sum of the two numbers. Okay. Now here is the table of X happens and its probability. Okay. So the capital X, so we'll record the sum of the number. So we already know that the range of the sum is from 2 to 12, right? From 2 to 12. Okay. So these are the range. The top line is the range of the random variable. Now the bottom, the line below the numbers are the probability. Is it true? For example, what is the probability to get the total sum 2? Just now we know there's only one way to get 2. You get extremely unlucky, right? You get 1, 1. Okay? So out of this 36, there's one chance to get 2. So this is 1 out of 36, right? Now let's do one more, and then so look at 3, right? I do the easy ones, right? So 3. What are the possibilities you get 3? You get 1, 2, or 2, 1, right? So you have two chances out of 36. So therefore, the probability of getting 3 is 2 over 36. And then you can try, right? It's symmetric. For example, here 11. So the way to get 11 is 5, 6, the combination of 5 and 6. So it's either 5, 6 or 6, 5. So you have two chances. Sorry, the first part I agree. So the second part, say it again. Yes. Yes. 2, 1. Okay, right. So that's why we have the 2 here. Right? Okay, no. Any other questions? Okay, good. So we have this table, but what we are trying to calculate? Sorry, is everything all right? Is there a question or? Which one? Sorry. 2, 5. Okay, so that I don't know. So maybe you are right. That I didn't. Okay, so okay, so let's calculate the expected value. So I want to do this, right? So the number, the probability of x hit this number x times the value, right? So we have to add all these. So the x will start from 2 all the way finish to 12, right? So I don't know. So this 36 certainly is right, but on top I didn't really try. So is it right? Correct. Okay, good. So if he says correct, it's correct. Okay. All right. So it's 7. Okay. So the expected value is 7. Okay. So let's take a break, and if you want to ask me something, ask me during the break. Okay. So we'll come back maybe in 5 minutes. Okay, so can we continue? Okay, so we are going to see maybe 2 or 3 more examples, and then we move on to the next topic. Okay, so we want to make sure we know how to calculate E of x, the expectation. Okay, so now let's try another example. So this time we toss a coin 5 times. Okay. So let's assume the probability of getting head is p, and the tosses are independent, whatever. So we want to find the expected number of heads obtained. So in this case, the random variable again counts the heads, right? So we toss it 5 times. So the range will be no heads or all heads. So from 0 to 5, right? So okay, so the solution for this is let's identify the random variable. So let capital X be the number of heads obtained in 5 tosses, right? This is a random variable. So let 1 minus p is q. So q is the probability of getting tail. Okay. Now again, we have this table. So the range, which is the possible value this random variable can take, is from 0 to 5, right? Because 0 stands for no head, 5 means 5 heads, and anything between can happen. Okay, so the range of the random variable are 6 values. Now we want to calculate the probability of each event, right? So for x equals 0, it means no it means no head, right? So it's odd tail. So we have 5 tails, T, 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 T. So in that case, the probability is Q to the power 5 because this Q is the probability of getting tail. So you get 5 tails, you get Q to the power 5, right? Let's choose here. So how about getting 2 heads? So first, the 2 heads can happen at different places, different tosses. So it's 5 choose 2. Right, 5 choose 2, you get 10. Now for each of the choice, you have 2 heads, so there's p square, right? And the other 3 coins are, other 3 tosses, you get tail, so it's q to the power 3, right? So this is the probability, okay? So now the expected value is just this times that plus this times that plus this times that, and you add them up, right? So, okay, so therefore the expected value is the sum from 0 to 5, right? So x can take from 0, 1, 2, 3, 4, 5, and multiply the probability, right? So we get this. So you sub everything in, and then you get this terrible expression. But however, there's a trick to simplify. You take out the common factor, you find out something like this. And this turns out to be p plus q to the power 4, if you know the binomial theorem. Okay. But p plus q is 1. So suddenly it becomes 5 times p. Right? But this is reasonable because, right, you toss the coin 5 times, and each time you have p possibility. So the expected value of return is 5 times p. Okay. All right, so this is another example. Now, before we do the last example, so we need to learn some properties of expected value. So this is one of the most simplest property called the linearity. Okay. So it says this. Suppose your random variable is a sum. Is in the form of a sum. So random variable x is actually is a sum of several other random variables. So let's say x is x sub 1 dot 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 plus dot 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 plus x sub k, right? So now each xi is a random variable. To calculate the expected value of x, actually is the same as calculate expected value of x1 and plus dot 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 plus expected value of xk. So this is called linearity. You can sort of, if you take e here, you can take e to each one of them and add them up. Okay. Okay. So if you care about proof, this is a proof. So let me quickly go through this. Right. So by definition, e of x is this. You know that already. But what is x applied to an event? Well, x is a function, right? So x will take an argument, but x is a sum. So x of s is just this, just x1 applied to s plus dot 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 plus this. Now by arithmetic, you get p of s multiply this, p of s multiply that, and so on and so forth. So you get the sum of these. But this will give you e of x1. This will give you e of x2, right? If you add them up, you get everything. Well, we don't care too much about proof, so this is just to convince you this is true. Okay. Okay, so now let's look at our next example where we are going to use this linearity. Okay. So here, motorist has a choice of 2 routes driving from A to D. Okay, whatever. Okay, route 1 says you have 3 stretches. So you have to go to B, and from B you go to C, from C you go to D. Okay, then for which the duration of travel in minutes is denoted by the random variable x1, x2, x3 respectively. Well, what does it say? Okay, so x1 will return how many minutes you finish from A to B. x2 will record the minutes you finish the stretch from B to C. x3 will do the from C to D. Okay? Now suppose for each of x, for k equal 1, 2, 3, the following probability are known. So for example, for x1, the probability you spend 5 minutes is 30%. The probability you spend 6 minutes on stretch 1 is 40%. The probability you spend 7 minutes on let's say k equal 1, on AB is 30%. Okay. This applies to all three stretches. Okay. On segment AB, 30% you spend 5 minutes, 40% you spend 6 minutes, another 30% you spend 7 minutes. The same for B stretch from B to C and from C to D. Okay, so this is the first route. The second route is, okay, a highway somehow by passing B and C. You directly drive from A to D. But the duration of the travel somehow is a random variable y, again calculated in minutes, is the possibility you spend 18 minutes is 90%. And the probability of you spend 23 minutes is 10%. Okay? Now what is the, which route do you prefer? Right? Is this okay? Okay, so then we calculate the expected value, right? So then that gives us the information. Okay, so time taken from route 1 is x equal, you have to add the 3 one, because you have 3 stretches, A to B, B to C, C to D. So you have to add x1 with x2 and x3, right? So the total time is x1 plus x2 plus x3. Okay? So we'll have the expected value for xk, for example, x1, because they are all the same, actually. So it's you have 30% for 5 minutes and so on and so forth, right? If you add them, you get 6. Okay. Now, for k equal 1, 2, and 3, you all get 6. So the expected value for x by the linearity, right? By the property we just shown, it is e of x1. I'm sorry, I should change it to square bracket. Sorry. I will revise it later. Okay. So the sum of these will be 3 times 6, you get 18. Okay. Now for the second route, the expected value, because you have 90% chance of spend 18 minutes, you have 10% chance of spend 23 minutes. So altogether, you get 18.5. So therefore, you are expected to spend more time if you take y, right? So this is better. Okay, so this is a simple example. Okay, so now we have to, I want to explain why expected value is important. So what does it tell us? So here, actually, this is a very deep theorem in probability. It's called the law of large numbers. Probably you have heard of it. Okay, so I'm unable to state the exact statement. It involves something like IID or so all these things. But this is a general education module. So let's say, so in probability theory, the law of large numbers, some people call it shorthand as LLN, right? Law of large numbers, LLN, is a theorem. It's a mathematical statement that describes the result of performing the same experiment a large number of times. So suppose you do something, repeat the same thing many times, and then you see some pattern. So the law of large numbers will tell you what you are going to see. Okay? So what are you going to see? So according to the law, the average of the result obtained from a large number of trials should be close to the expected value. Right? So that's the importance of expected value. So if you repeat the thing many times, you are going to see the expected value. Right? So, and the more, how to say, the more trials you perform, the closer to the expected value you get. So this is the law of large numbers. Right? So that explains why the expected value is important. Right? Intuitively, expectation is the long-run average value of repetitions of the same experiment. Right? If you do it over and over again, you are going to see the expected value. Okay. You'll learn the exact statement of law of large numbers, not in this course, in some other courses. Okay. Since we are here, so let me make this tiny remark. You see, the probability you can think of is useless because it tells you maybe, how to say, 90% something will happen, right? But okay, even it is 100%, it tells you it may happen. It could not happen. I mean, it's possible that you are so unlucky, even it's 100%, you can still, right? So, especially when the sample space is infinite. So you could have this, or you can say, let's don't take an infinite thing. Let's say you have 99.9% something happen. But suppose you want to do your action based on this probability. You are never sure whether it will happen, right? So in some sense, it doesn't help. But no, it will help in the long run, right? So the law of large numbers will tell you that although I don't know for sure that this thing will happen in this trial, but if you repeat the same thing over and over again, the pattern will show up, right? Suppose you do it. Suppose, for example, for the previous example, suppose you make the trip every day, and then it will follow the pattern because the law of large number will tell you that the route 1 is shorter. You spend less time, right? Maybe for the single trial, you may spend more time. But if you do it over and over, the law of large number will tell you the expected value will show up, right? So probably I don't need to say this. It's so intuitive, right? So it's okay. Okay. So now back to the example at the very beginning, right? The strange offer, right? So somebody offered you 1,000, and also there's another choice involves some randomness. So what do we do? So we'll try to calculate the expected value of the second option. The first option, we know the return. We know the payoff, right? So it's $1,000. For the second, the expected value is because you have 90% get this 1,200, but you also have 10% to get minus 100 because you have to pay him 100. So the expected value is this, right? 1,070. Okay. Now the law of large number will say, if you repeat this offer many times, you are going to get closer and closer to this return, 1,070, right? So therefore, certainly in the second option, suppose you are offered this every day for a year, you should take the second option, right? Now I don't know for the first option, it depends on, are you a gambler? I mean, depend on your personality, right? So if you don't want to lose anything, you want to play safe, you take first offer, right? But if you think 90% is good enough, you want to take the risk, well, go ahead. So this part probability will not help you. But for the 365, if you repeat it that many times, well, maybe the probability will give you some help. Okay? So that's the answer for the motivating question. So now I want to show you okay, so now we move on the last topic of today. It's very fun. I don't know whether some of you may have heard of it. But, okay, so forgive me to show you some video from internet. Okay, so this is what I'm talking about. Okay, I don't know how. Okay, so let's. Whatever. Okay, so let's skip this. Okay. Can you hear? Wait. I need. Can you turn on the speaker? I don't know how. Maybe it's somewhere here. Can you see it? Or? If you have a computer, lots of you have it, and you can click on there's a hot link. So let's don't destroy that. So this is, maybe this is right. No? Does anyone know how to turn on the speaker for this? No? Well, you can watch it. I will repeat the same thing, but in a video form is better. Okay, so for those if you want to commit fraud, okay, whatever. So sorry, I'm. Okay, so let's look at real thing, right? Okay, so we are looking at some data. Okay, so we say a set of data, a set of numbers satisfy something called Benford. I'm going to show his picture in a second. Benford's law, if the leading digit d belong to, okay, d is from 1 up to 9, right? So you look at, so you have a table of data. and you look at the first digit of the numbers in the table. Okay. Now, if it follow this pattern, then we call this set satisfy this law, Benford law. So what is the pattern? So the probability of the d equal 1 is 30%, is equal to this, right? You plug in 1 here, so it's log 2 minus log 1, which is 0, so it's log 2. So it's more or less this. Now the digit for 2, in your data, the first digit is 2, the frequency is this much, right? And this is 3, 4, 5, all the way up to 9. Suppose your data fits this, and then it's called, it satisfies Benford's law. If you suddenly have this part very high, and then it doesn't satisfy. Okay, so now, so let's look at some history. This is funny. So here are two, this is Benford. Okay, so the so-called Benford law actually was discovered by this guy. So this guy in 1881. And what he noticed is very funny. So he looked at, okay, before you have this computer, your mobile phone, there are some, when people look at, when people want to calculate log, they don't punch their calculator. There's a table. There's a book called Table of Log or whatever, right? So he noticed in 1881, he noticed that in the book of logarithm tables, somehow the first part, right, the front pages are heavily used, right? So if you look at the book, you know that maybe they are curly and so they are not so clean, right? So the front pages of the book on logarithm tables were more significantly worn out than the later pages. Okay, so he noticed this. Now, what's the reason? Why we see more use of the front pages? So roughly, we can explain this way. So when we make logarithm table, sort of we list the log uniformly. So you list the value of log like 0.1, 0.2, 0.3, 0.4, and so on. And maybe it's much more, 0.01, 0.02. And so you list them uniformly. Now let's look at, for a number, let's only look at number between 1 and 10. Why? Because, for example, here I should type for example. So for example, we have this number which is far beyond 1 and 10. But when you create log table, suppose you are only interested in log of this, you can write this as that, right? When you take log, only this part important. This part will become 4. It's an integer. You know how to calculate. So it is the log of this which you are more interested in. So therefore let's only consider the logs of something between 1 and 10. Okay? So now this is an obvious fact. So the x star with a digit 1, so this is the case x star with digit 3. So only when x is between 1 and 2, obvious, and so on and so forth, right? Now, x star with 1, look at this. Because the property of log, if and only if the log x is between log 1 and log 2, right? So this is trivial, right? You take log here. Okay, so x star with 9, if and only if log x is bigger than or equal to log 9 and less than log 10. Okay? So the interval of log 1 and log 2 is much wider than interval log 9, log 10. Right? The first one is roughly 30%. 0.3. The length of this is roughly 0.05. Actually, that's the Benford law. So this is about 30%. This is about 5%. Okay? So this is better. So you see the x between the first digit between 1 and 2 should appear here. This is 30%. And then it's diminishing. So last part is 0.5%. Okay? Okay, so the guy knew somewhere in 1881 discovered something like this. Now what Benford did is Benford looked at other data, not only log. He looked at funny data like, I don't know, surface area of rivers, populations, whatever. So he looked at other data, and he find that other data somehow also fit this his Benford law, also fit this pattern. Okay, so but however, no reason, right? So this is not a mathematical theorem because it depends on your data, right? For example, if I look at the exam score, it definitely won't fit this, right? If the exam score look like this, I'm in trouble, and you are in trouble. Okay. Okay. Anyway, so this is not a theorem, but many funny things come from this. Okay. So how can this help us? So for example, it can help us determine a better way to store numbers. If you know that this kind of number has more frequency to appear, you'll probably leave more room for them, right? So that you save some space. You don't leave lots of space for 9 point something. Instead, you leave more space for 1 point something, right? So, and also, this is the funny part, right? Detecting fraud and data integrity, right? So here is so here's a test for you. So I'll show you. So this is the country name, and this is the area of the country. Okay. So there are two columns. I have two sets of data. Okay. Now one column of this table gives the real surface area of the country, then the other is fake. Okay. Now which one is real? Which one is fake? Good. Okay. So no, because you know Benford law, right? So because you know that this guy has no single one appear, is unlikely, right? So, okay. So you know which one is real. Okay. Now this is actually people working in the financial, I don't know, the tax bureau, or they actually use this to catch the criminals or the frauds, right? So I say John Smith or whoever. Okay, so he's a salesman, and he tried to claim money, right? So he used his receipt and try to. So he cheats, right? So you look at the receipt, he'll inflate the bill. So what he does is where is it? Right. So he regularly change the digit from a smaller number to big number, right? So that he claim more money. So he changed the 1 to 4 or 7 or 9. So for example, $18 meal will become 48, right? So it just change, okay? But if you do this, you violate Benford law because you move the smaller number to the, so it's more likely you see larger numbers, right? So then the police somehow, so that's why the video was saying that if you want to commit fraud, right, you better learn something. Okay, so you can, on internet there are more explanations and more examples like this. So have fun, and that's